All right, welcome back everybody. In this video, we're going to talk about section 9.5 of AP Calculus BC, integrating vector-valued functions. We'll get right down to it. First off, the indefinite integral of a vector-valued function is another vector-valued function where we take the antiderivative of the vector-valued function r, and it results in the antiderivative vector-valued function plus some constant vector. And, with all the different ways we have of notating vectors, we could write these in a lot of different ways. I'm going to lean towards component form since that's the most common. But in essence, when we have a vector-valued function r of t and we integrate it, we integrate each of the components. And when we do that, we find the antiderivative of that particular component plus a constant of integration. And so we'll end up with a vector-valued function where the components are the antiderivative of the original component plus a constant. Same thing there. Or we can do it in standard unit vector notation. That's what it looks like there. And then we can combine these into we can combine our I vectors into one and our j vectors into another. Sometimes you might even see this, this integral written in this form up here as well, and then calculate the constant vector from there. Lots of different ways. I'm going to focus on doing it in component form. So let's go ahead. We're going to find our vector r for dr dt equals negative sine of t comma cosine of t. So all we've got to do is we find the antiderivative of negative sine of t. That's going to be cosine of t plus a constant of integration. And then we find the antiderivative of this component. That's going to be sine of t plus a constant of integration. Now you folks who know me well know that I am loath to subscript my constants of integration, but when I do these with vector-valued functions, I'm going to do that because I have multiple constants going on at once. Instead of a constant that's changing to a different constant, changing to a different constant, it's multiple constants going on simultaneously, so I will subscript my constants in this situation. All right, part B. We're going to go ahead and integrate this vector-valued function. And so we take the antiderivative of both of the components here. The antiderivative of 1 over t squared is negative 1 over t, and again, plus a constant. And the antiderivative of t cubed is going to be 1/4 t to the 4th, plus a different constant. And so that's what our indefinite integral of that vector-valued function looks like. All right, example 2. Solve the initial value problem. So here we're looking for a vector, and we're given the derivative of that vector, and we're given an initial value vector where the vector at time 0 is the vector 1, 1, which is going to enable us, when we take the antiderivative of our derivative vector, it's going to enable us to solve for these constants of integration to write the one specific vector that meets both of these characteristics. So we start by taking the antiderivative of that function. And so we've got r of t is equal to, and the antiderivative of 1 over t squared plus 1 is the arctangent of t plus our constant. And the antiderivative of t over the square root of t squared plus 1. If we think about this, we could do this via substitution if we wanted to. This is u equals t squared plus 1, etc. But hopefully you've started to recognize by now that all this is the antiderivative of that's just the square root of t squared plus 1. Hopefully you've seen that enough by now in your life. And now we've got our second constant for the y component. And now we're going to use this initial condition vector in order to solve for c sub 1 and c sub 2. And so that means that at time 0, we want the arctangent of 0 plus c sub 1 to be equal to 1. The arctangent of 0 is 0, therefore c sub 1 is equal to 1. And then we look at the y component. We've got the square root of 0 squared plus 1 plus c sub 2 being equal to 1. Square root of 1 is 1, so c sub 2 is going to be equal to 0. Now that we've found those constants, we can go ahead and write our final vector-valued function. which is going to be the arctangent of t plus 1, and the square root of t squared plus 1. And there is our vector valued function to finish off example number 2. All right, on to the next page. Now we're going to look at the definite integral, and actually I think the definite integral of vector valued functions is even easier than the indefinite integral of vector valued functions. In essence, all we need to do is take the definite integral of each individual component. I've written it in standard unit vector form here, but the same thing applies. We take the integral from a to b of f of t dt, which we get by taking the antiderivative and evaluating it at the limits of integration, and that's going to give us our vector valued function for the definite integral. Now, of course, the definite integral of a vector valued function, instead of being a function, is just going to be a vector. So I'm going to do that based off of whatever form they're written in. The first one here, we've got the integral from 0 to 1 of 3 plus 6ti plus 6 pi cosine of pi tj. So we're going to take each of those components and integrate them individually, and then multiply the result of that times the standard unit vector. And we're going to take the integral from 0 to 1 of 6 pi cosine of pi t dt and multiply that times the standard unit vector. And so now we want to take the antiderivative here. It's 3t plus 3t squared. There. And the antiderivative here is, let's see, that's going to be 6 sine of pi t. And then we're going to evaluate those at the limits of integration. So we end up with 3 plus 3, which is 6, minus 0. We end up with 6i. And then this is going to be 6 sine of pi. Sine of pi is 0, so that's going to be 0. And then 6 sine of 0, that's also 0. So we end up with 0j. So guess what? I don't even need that plus sign. My vector is 6i. All right. Last example, example 4. We're going to take the vector v of t. We've got it in component form this time, so we're going to go ahead and write it in component form. So we've got the component integral from 0 to 1 of e to the negative 2t dt, and then the other component is going to be the integral from 0 to 1 of 1 over t plus 3. And now we just need to find the antiderivatives of those. The antiderivative of e to the negative 2t is negative 1/2 e to the negative 2t, which we're going to evaluate from 0 to 1. And the antiderivative of t plus 3 is the natural log of the absolute value of t plus 3, which we're going to evaluate from 0 to 1. And that'll enable us to find our components here. We've got negative 1/2 times e to the negative 2 minus negative 1/2 e to the 0, and we've got natural log of 4 minus natural log of 3, and we'll clean those up, and that is going to give us our component form and our definite integral of the original vector function from 0 to 1. All right, everybody, that brings us to the end of section 9.5. Join me next time for section 9.6, where we are going to solve motion problems using parametric and vector valued functions. All right, see you next time. Have a great rest of your day. Bye-bye for now.